Now let's look at the important concept of process yield to measure the level of defects in a process. We'll use P to represent the number of defective units produced at a process step, divided by the total number of produced units going into the process step. This is also known as the fraction defective, I have here, or sometimes called the defect rate or the failure rate. Sometimes you hear those terms. And if you convert that into a percentage, then we get the percentage defective. Okay. So, on the other hand, the yield at a process step, which represents the number of good units produced at that step divided by the total number of units going to that step, is going to be equal to 1 minus P. So 1 minus P is the percentage of units that complete a sub-process or a part or a process step meeting quality guidelines without being scrapped, retested, or reworked. So if you have more than one process step or more than one part to make your product, where N is the number of process steps or parts, then the overall good units coming out of the entire process is going to be the process yield, or the yield at each process step, 1 minus P to the power of N. Now just a note here, we're going to use the term process yield. But this is also referred to as, for example, first pass yield or first time yield or rolled throughput yield. And these are sometimes used interchangeably, although typically rolled throughput yield is normally given as the probability of manufacturing a part or performing a service process that you can perform all the required steps without any failures. Whereas first pass yield does not normally consider that, but it depends on the reference. We're going to call it process yield, means the yield at each step, 1 minus P to the power of N, where N is the number of steps. And just one variation on that is if you have different yields at each process step. So yield at step 1 is we call A, yield at step 2 is called B, yield at step 3 is called C. You multiply all these three together to get the process yield. So let's do some examples. Here we have a 3-step process, and the process yield defined as the good parts out divided by the total parts in. So for example, if we start with 10 parts into process step 1 and get 10 good parts out, then the yield is going to be 10 over 10 or 100% for that process step. For process step 2, we have 10 parts going in and only 9 out. So the process yield for step 2 is going to be 9 over 10 or 90%. For step 3, those 9 parts go in and 9 parts come out. So here we have process yield of 9 over 9, also 100%. The total yield, as we learned, we have to multiply all the yields together. So we have 100 times 90 times 100, and we end up then with an overall yield of 90%. And we can also say, I've written over it here, good parts out is 9, parts in is 10, 9 over 10 is 90%. Okay, so let's look at the 3 process step then with each 10% fraction defective and calculate our final process yield. So we said that the fraction defective is equal to P. So P is equal to 10% or 0.1. We have 3 process steps. N is equal to 3 here. And this means then we have the fraction good parts coming out of each step is 1 minus P. 1 minus 0.1 is 90% or 0.9. And we can then calculate 0.9 to the power of 3 to give us an overall process yield of 73%. do another example. Here we have a 3 process step with a fraction defective at each process step of 1%. So, since 1% of the production of each process step is defective, P is equal to 0.01. And the yield, again, we're going to have at each process step is 1 minus P, or 99%. So we calculate this as 0.99 to the power of 3. And what do we get here for our overall process yield? Much better, right? 97%, better than 90%. Process yield at each step, where we only stuck with 73% out, now we have 97% out. So now let's look at a 10-step process. We have at each step 10% fraction defective. So P is equal to 0.1. 1 minus P, the yield at each step, is equal to 0.9. How do we calculate this? Before 0.9 to the power of 10, and we end up with only 34.9 good parts coming out of our process. You know where we're going next, right? We have 10 process steps, each with 1% fraction defective. So P equals 0.01. 1 minus P equals 0.99. 99% percentage defective at each process step. Now we have 0.99 to the power of 10, and we end up with, yes, a better result, 90.4% yield overall, process yield. For 100 process steps, each with 1% fraction defective, what is your final process yield? So here you have P equals to 0.99, 0.99 to the power of 100, only 36.6% good parts out. For 1,000 process steps, each step with 0.99, 99% yield. Our overall process yield is 0.00432%. And what if we have 10,000 process steps, each with 99% defective, 1% fraction defective at 99% yield? Pretty much zero end process yield. By the time you take 0.99 to the power of 10,000, you don't have any good parts out. Now, why is this relevant? What could this be? Well, since we work in Bavaria, assume a car consists of 10,000 parts or processes. Let's look at this. For 10,000 process steps, each with 1% fraction defective, each with 99% yield. So we just said, you don't get any cars out. What can we do? Let's improve that fraction defective. Let's make it 0.621. So instead of 1%, we've improved the fraction defective to less than 1, to 0.621. Well, if we do that, what do we end up? Well, pretty much zero. Pretty much nothing comes out of our process. What happens if we go to extreme measures and each process step has only 3.4 times 10 to the minus 4th fraction defectives, meaning that each process step has 99.99966% yield. What do we get? Well, if we do that, 99.99966% to the power of 10,000, we end up with 97 good parts. What you're supposed to see here, these numbers are chosen purposefully, that you have to have a very, very low fraction defective when you have a complex product in order to get a reasonably high yield. And think about 97% for BMWs. How much does each BMW sell for? And so if out of every 100, we only have 97 that are good, we're losing 3% of our production every time, for example.